Hello everyone, my name is Tanvir and today I'm here to speak a few words on the Chitosan, a natural biopolymer with a wide range of applications. Introduction. Water is the most important natural resource of the planet Earth, and its purity is vital for humans. Currently, the entire world is facing the most challenging issue: water contamination with different pollutants. Researchers and scientists are trying to overcome this emerging problem by seeking new materials with great absorbent properties, and one of them is the Chitosan. Chitosan is a natural polysaccharide biopolymer which has been widely used in different processes and applications. Chitosan-based membranes have been used in reverse osmosis, gas separation, dialysis, and pervaporation. It is made by treating the chitin shells of shrimp and other crustaceans with an alkaline substance, such as sodium hydroxide. Chitosan can be used in hydrology as a part of filtration process. Chitosan causes the fine sediment particles to bind together and is subsequently removed with the sediment during sand filtration. It also removes heavy minerals, dyes, and oils from the water. As an additive in water filtration, Chitosan combined with sand filtration removes up to 99% of turbidity. Chitosan is among the biological absorbents used for heavy metal removal without negative environmental impacts. History of Chitosan. The human use of Chitosan can be traced back to 1811 when chitin, the source from which it is derived, was first discovered by Braconnot, a professor of natural history in France. According to historians, while Braconnot conducted research on mushrooms, he isolated what was later to be called chitin. Some 20 years later, an article on insects was published, which noted that a similar substance was present in the structure of insects and plants. The author called this substance chitin. Basically, the name chitin came from the Greek word meaning tunic or envelope. In 1843, Lassagne showed the presence of nitrogen in chitin. After the discovery of chitin came chitosan. It was first observed by Rouquet during his experiments on chitin. Rouquet observed that the compound of chitin could be manipulated through chemical and temperature treatments and become soluble. In 1878, Lederhose showed chitin to be made of glucosamine and acetic acid. It was not actually until 1894 the substance was named Chitosan. By the early 20th century, a great deal of research had been performed on the subject of Chitosan. It involved the sources of chitin, specifically crab shells and fungi. It was the work of Rammelberg in 1930s that led to the confirming Chitosan in these sources. Experts determine by hydrolyzing chitin that chitin is a polysaccharide of glucosamine. In 1950s arrived, the X-ray analysis advanced the study of chitosan in fungi. Only recently has technology proved reliable in identifying the presence of chitin and cellulose in cell walls. The first book on chitosan was published in 1951, 140 years after Braconnot made his initial observations. In the early 1960s, chitosan was studied for its ability to bind with the red blood cells. The substance was considered a hemostatic agent. For 3 decades now, chitosan has been used at water purification plants for detoxifying water. It gets spread all over the surface of water, where it absorbs grease, oil, and other potential toxins. Discovery of Chitosan. Chitosan was discovered by Roquette in 1859 after heating chitin in an alkaline medium. Several years later, Hope Sayer called this material Chitosan, although its chemical structure was not elucidated until 1950. In recent years, Chitosan-based materials have been developed due to their particular chemical properties, which provide it a wide range of applications. Generally, Chitosan is highly soluble in acid solution, mainly below pH of 6.0, being a weak base pKa 6.3 due to the presence of amine groups. At low pH values, the amine groups are positively charged due to protonation, so Chitosan can be a water-soluble cationic polyelectrolyte. However, when the pH increases above 6, the amine groups of Chitosan residues are deprotonated and the biopolymer loses its charge, leading to an insoluble polymer. Formation of Chitosan. After cellulose, chitin is the second most abundant biopolymer and is commonly found in invertebrates as crustacean cells or insect cuticles, but also in some mushroom envelopes, green algae cell walls, and yeasts. At industrial scale, the two main sources of Chitosan are crustaceans and fungal mycelia. The animal source shows, however, some drawbacks as seasonal, of limited supplies, and with product variability, which can lead to inconsistent psychochemical characteristics. The mushroom source offers the advantage of a controlled production environment all year round that ensures a better reproducibility of the resulting Chitosan. The physical properties of extracted Chitosan being notably related to the growth substrate composition. Moreover, the vegetable source is generally preferred to the crustacean one from an allergenic point of view, the produced Chitosan being safer for biomedical and healthcare applications. The mushroom extracted Chitosan typically presents a narrower molecular mass distribution than the Chitosan produced from seafood, and may also differ in terms of molecular mass, DD, and distribution of desilate groups. Chitosan DD greatly varies between 60 and 100%, while its molecular weight typically ranges from 300 to 1000 kDa, depending on the source and preparation. Chitosan oligomers can be prepared by degradation of Chitosan using specific enzyme or reagent as hydrogen peroxide. At the time of its production, it is difficult to predict Chitosan characteristics. Therefore, the current approach consists in analyzing the resulting product composition and properties rather than in targeting predefined characteristics by controlling the process of production. The characterization of Chitosan is thus quite of importance, but it is not easygoing or straightforward. Being a natural based compound, Chitosan may be contaminated by organic and inorganic impurities and presents broad polydispersity. This is why producers mainly refer to samples viscosity rather than molecular mass. Chitosan is also poorly soluble except in acidic medium, which makes analysis difficult to perform. Different methods, including pH potentiometric titration, IR spectroscopy, 1H NMR spectroscopy, but also UV spectroscopy, colloidal titration, and enzymatic degradation, are reported in the literature for the determination of Chitosan desiccate degree, while its molecular mass is typically deduced from viscosimetry or determined by size exclusion chromatography. So here's a flowchart showing the production of Chitosan right from crustacean wastes, and this is it. Applications of Chitosan. Some applications of Chitosan in biomedical and pharmaceutical material are as follows: treating major burns, preparation of artificial skin, surgical sutures, contact lenses, blood dialysis membranes, artificial blood vessels, anti-tumor, blood anticoagulant, antigastritis, hemostatic, hypoglycemic agent, antithrombogenic agent, drug and gene delivery systems, dental therapy. Some applications of Chitosan in tissue engineering are as follows: cell growth and proliferation in tracheal cartilage, nerve, bone tissue repair and regeneration materials for cartilage repair, porous 3D scaffold of Chitosan hydroxyapatite composites for bone regeneration, Chitosan chondroitin sulfate sponges in bone regeneration, Chitosan calcium alginate capsules to develop artificial pancreas for diabetes mellitus treatment. Antibacterial property of Chitosan. Chitosan is largely known for its activity against a wide range of microorganisms, in which the most acceptable antimicrobial mechanism is found to include the presence of charged groups in the polymer backbone and their ionic interactions with bacteria wall constituents. This interaction suggests the occurrence of a hydrolysis of the peptidoglycans in the microorganism wall, provoking the leakage of intracellular electrolytes, leading the microorganism to death. The charges present in Chitosan chains are generated by protonation of amino groups when in acid medium, or they may be introduced via structural modification. This latter can be achieved by a methylation reaction resulting in a quaternized derivative with a higher polymeric charge density. Since the charges in this derivative are permanent, it is expected as a most efficient antimicrobial activity. Hence, in the present study, commercial Chitosan underwent quaternization processes, and both were evaluated in gel form against Staphylococcus aureus gram-positive and Echinacea coli gram-negative as model bacteria. The results as acquired from turbidity measurements differ between materials with an expressive reduction on the gram-positive microorganism growth, while E. coli strain was less sensitive to both polymers. Additionally, the antibacterial effectiveness of Chitosan was strongly dependent on the concentration, what is discussed in terms of spatial polymer conformation. Pervaporation using Chitosan-based membrane. Pervaporation is a separation method where a liquid is transported through a non-porous lyophilic membrane. This membrane is responsible for removing some components in their vapor state into a vacuum or inert carrier gas. An efficient pervaporation membrane should be characterized by a good mechanical durability, chemical resistance, high selectivity, and high permeate rates. Taking into account these considerations, Chitosan is a hydrophilic material under acid conditions, which can react through its hydroxyl and amine groups with several functional groups such as epoxy groups. The hydrophilic groups can play a key role in the preferential H2O sorption and diffusion through the Chitosan membrane. Thus, Chitosan has been proven to have good film forming properties, high water permeability, and chemical resistance. Conclusions: Chitosan is a natural polymer with tremendous biological properties such as biocompatibility, biodegradability, and anti-infective activity, among others, due to its high charge density. The existence of reactive hydroxyl and amine groups or its capacity of interact with other polymeric fractions through hydrogen bonds. These interesting physiochemical properties and the capacity to functionalize the amine and hydroxyl groups for specific uses has attracted the interest of the scientific community in the last decades to study and develop interesting applications for Chitosan. Chitosan and Chitosan based composites have enormous potential in medical applications such as burn treatment, artificial kidneys, blood anticoagulation, and bone, tendon, or blood vessel engineering. However, the tunable capacity of Chitosan takes this biopolymer to applications beyond medicine. Thus, other challenges for the future are focused on the developing of nanocomposites for applications in biosensors, packaging, separation processes, the food or agricultural industry, and catalytic processes. Another challenge is related to the valorization of Chitosan into valuable organic compounds, which usually are obtained as alternatives to traditional fossil fuels. One of the main challenges for the use of Chitosan in the future must be the optimization of its degree of decetylation using environmentally benign reagents. Another key parameter is the design of modulated tridimensional Chitosan structures by cross-linking processes which improve its use in specific applications. From a catalytic point of view, a main challenge is how to design porous Chitosan-based catalysts to increase the amount of available active sites and thus improve the efficiency of catalytic processes.